Okay, here's another YY fundy thing. This is YY fundies. And we're really talking about V and I relationships. Okay, the last problem was just V's. Now we're talking about V's and I's. So we've got a YY connected circuit. So let's draw that. We've got 3 voltage sources and their impedances. And this comes up to a little terminal A, little terminal B, little terminal C, and then the neutral terminal. And these guys go over to 3 loads. So this is ZA to neutral, and this is ZB, big B. This is ZC. This goes to big terminal C. This goes to big terminal B. And these are connected. And these are connected. All right, so we've got ZA, ZB, and ZC impedances, and they're the same. They're balanced. Although it doesn't, do they tell us that? Yeah. This is about, they have to tell you this is a balanced 3-phase load. They have to tell you that, because if it's not balanced, then, well, if it's balanced, then the voltages and currents for each phase will be off by 30 and 120 degrees, but only if it's balanced. Well, okay, that's not really true. I mean, the voltages are off here by 120 degrees and 30 degrees. The voltages have a relationship here, if they're balanced. But then the loads, if the loads are balanced, then the currents will be balanced. And if the loads aren't balanced, then the currents won't be balanced. But typically the voltages are always balanced over here. Anyway, I'm probably talking too much about that, but it's a balanced 3-phase load, all right? So they're giving a, so that's this balanced 3-phase load. Then it has the single-phase equivalent. So I think this problem, I can't remember where it came from, but I think what's given is this single-phase equivalent of a balanced 3-phase load. So I'm drawing this just for my own edification, your own edification. But I think what they actually gave you was this single phase equivalent down here. So here it is. It's it's a balanced load, because if it's balanced, you can model it like this. You can model the neutral conductor. In here, I left it off. I mean, you can draw it as a dotted line in here. If it's balanced, then there will be no voltage potential across here. Therefore, there will be no current through here if it's balanced. All right. But for analysis purposes, we can throw this guy in here. So in reality, in the 3-phased circuit that which is what's, the big picture is this 3-phase circuit. The current's coming around through, say, A phase and then coming back through these other phases, right? It comes in through A phase and then out through the other phase for one instant in time. And then later on, it might come this way and go back the other way like that. But it never goes through this guy. So here, we can draw the single-phase equivalent, okay? But let me just draw that. But the current that's in it is sort of really going through these other 2 guys. I'll come back and say that again in a minute. But look here, there's this thing here. There's this in here, the impedance in the load. So let's call this A prime. This is to terminal A, right? And then there's this the impedance in. There's an impedance in here which I didn't draw. Impedance in the line is this thing here. It's a resistance, and then this guy, and that goes over terminal A. And then there's this resistor here and an impedance here and an inductor here. And they give you values for all of these things. So this is J28 ohms. This is 39 ohms. This is J 1.5 ohms. This is 0.8 ohms. This is J 0.5 ohms. This is 0.2 ohms. So what do we got? We got a voltage source. This is V sub little a n, or little a n prime n, I guess. So this is given, it's 120 angle 0 degrees. This is sort of our reference voltage. Then the impedance in the generator is these two items. The impedance in this distribution line is these two items. And the impedance in this load, ZA, is these two items. And the magnitudes reflect that. Like the load is 39 and 28. That's a pretty big number compared to 0.8 and 1.5, the distribution line. And then an even smaller number is the wires inside the motor, this 0.2 and 0.5. Okay. So we're looking at the single phase equivalent. We're looking at just this loop right in here. So here we're modeling, and this is a model, right? We're modeling this center conductor as the return path for the current around this A loop. Okay? But in reality, the return path for this current around the A loop is really going through B and C back to the generator. Okay? Right? Well, let me just say that again. The current comes out here and goes around, gets to this point, and then it goes back through B and C, depending on who has the most where the negative voltages are. It's going to go that way. It won't go through here. But we're going to put that in here just so we can solve for the current. So there's a current through here. This is I sub A. What are we trying to find here? So this is, all this stuff is given, all of this stuff in here. But we're trying to find a bunch of stuff, all right? We're trying to find, this is a messy problem. I'm sorry about my organization here. I apologize. But we're trying to find the line currents, IA, IB, and IC. All of those guys, okay, and we're trying to find VAN, VBN, and VCN, and then we're trying to find VAB, VBC, VCA. Okay, so all of the three current. So this is I sub A here. This is I sub B, and this is I sub C. We're going to find those three line and phase currents are the same thing. There's just these three, but there's 6 voltages. There's line to neutral, 3 line to neutrals, and then 3 line to lines. And we're using the single phase equivalent, the single A phase equivalent, to find the rest of these guys. Because once we find this is VAN over here. Plus minus. Once we find VAN and IA current, then we know the relationships for all of these others in here are just some angle apart from all of these for a balanced circuit. Okay, so to do the I's, we're just going to use Ohm's law for the total loop, the total loop A. So so basically I sub A is V sub AN over Z total, right? This voltage here is pushing across this in total impedance, right? And then we're back here. You know what? It's kind of neat to think about this. So this is a model. This is just a model. It's only a model. The Monty Python said. We're modeling it as a wire. That is to say, there's no impedance in here, right? If it were a wire, a miles long wire, then we would have to put the resistance and the impedance and the reactance in here. But we don't, because this wire is not actually here. The current's actually going back through these other phases. you know. it's a little bit weird. These other phases have impedances, but I mean the way it works out is, the model wise, that this is just a wire. That's about all I can say right now without getting too crazy. Maybe go back and look at what I was saying on the summary video of the chapter. But anyway, just moving on. This current is this voltage here over this total thing. So it's going to be 120 angle 0 is the voltage, and then add up all of these guys. So it's 0.2 plus 0.8 plus 39. That's the resistances of these, the windings, the distribution line, and the load, plus the J times the reactive parts of those three elements. All right, and answer is 2.4 angle minus 36.9 degrees amps. That's I sub A, which is one of our answers. And then we know that the other three currents are just out of phase by 120 degrees. If this was IA and it's minus 36 degrees, then we can, you can just add and subtract 120 degrees. So I sub B is 2.4 angle 156.9. Just add 120 to this, right? And then I sub C is 2.4 angle 83.1 degrees. Just subtract 120 degrees from that. So that's the two answers there. Line in there. So that was these answers right here, IA, IB, and IC. We just used the single phase equivalent to get IA, and then realize that the other two currents are off by 120 degrees. So the same angle difference is true for the phase voltages which were given here. So this is the source, little an prime, little n. Actually, we need this guy, V sub an. So for the V sub an, we're going to use Ohm's law, but just at the load, at Z sub A, big AN. Just use this because we got I, so use this in here. So V sub an by Ohm's law is I sub A Z sub an. So it's 2.4 angle this one minus 36.9 times this impedance over here, and I got it in polar, 39 plus J 28, and that's the answer is, it's 115.22 angle minus 1.19 degrees volts. Then we've got this pretty picture over here. This is a minus 1.9. So let's see, is the X, it's too much, but this is 1.19 that away, minus, because we're doing clockwise ness. So this is VAN, and VBN is going to be 30 degrees. This is AB rather, and then this one's a little bit after the vertical here. So this is VBC, and then this guy's over here, and then there's there's this one, and then there's this one. So this is VBN, and this is VCN, this is VCA, and this is VBC. So root 3 times the magnitude here, 115.2 is 199.58, and that's the magnitude of this guy compared to the magnitude of this guy. It's root 3 bigger. And this guy's 30 degrees before this guy, so minus 1.19 minus 30 equals 28.81 degrees. That's this angle here. This guy here is 28.81. So V sub AB is 199.58 angle 28.81 degrees volts. All right. Kind of a mess. Sorry about that, but that's it. And then the other guys are just off by the same, or by 120 degrees. So 199.58, all have the same magnitude. Angle. This is, so this add 120 to this, you're going to get, or let's see, I'm going to do these right. Shoot. BC. This guy. You're gonna subtract 120 because these three line to lines are 120 apart. So you subtract 120 from 28, you get minus 91.1. And if you added 120 plus 120 and minus 120 to get CA, add 120 to this, you're going to get 148.81. Okay, sorry about the little messiness, but let's just go through this here. So you're given this single phase equivalent. You're told that it's balanced. So, and you're given this source voltage for one phase, and you're given the impedances for one phase. You can use Ohm's law twice to get this voltage at the load, V big A N, and the current through that loop. And then you just apply these angle relationships on IA and VAN to get the phase, or the line-to-line voltage from the phase voltage. Yeah. All right.